So, let's start today's journal club. Today's topic is quantum computer for simulating infection spreading. First, let's read abstract. Did you finish to read the abstract? So, can you find the gap sentence?
There's no clear gap.
I think so. No gap sentence. But they didn't clearly write gap sentence. But I think one of the motivation of quantum computing is computational efficiency. They wanted to compute something efficiently. It's I think it's a general statement. By the way, did you check this year's Nobel Prize? This year's Nobel Prize is macroscopic quantum mechanical tunneling. In classical physics, the ball cannot go through the wall. It's bound. But in quantum system, the ball can go through the wall. But usually it's very, very tiny scale, it's nanoscale. But this year's Nobel winner found macroscopic level. It's meter scale. So this discovery is one of the key technologies for quantum computers. So this Nobel Prize was announced last week. So this week is the best timing to learn. But I'm not a physicist, so my explanation may not be exact. So my explanation will be intuitive. And they applied a quantum computer to infection spreading process. The simplest model for infection spread is SI model. It's very simple. Susceptible person interact with infected person, and he or she will be infected. It's very easy, and everyone can simulate. So the quantum computer is not required. In network level, SI model can be written as this. Beta is transmissibility, virus transmissibility. It means the nature of virus. And kappa ij is contact patterns. It's the strength of interaction. But it's also easy. So what is the motivation of quantum computing? Stochastic process. Susceptible person is labeled 0, and infected person is labeled 1, and P0 of T is the probability of susceptible person, and P1 of T is the probability of infected person. The time evolution of the probability function is modeled using Markov model. But if we consider one person, it's very easy. The transition matrix is 2 by 2, and we can analytically solve this process. And then we think two people. The transition matrix is here. The size of transition matrix becomes 4 by 4. But 4 by 4 is not so difficult. And then we consider 3 people. Transition matrix becomes 8 by 8. It looks complicated. And in general, we consider n components. The transition matrix becomes 2 to n by 2 to n. It's very large. So the size of transition matrix grows exponentially. So I think gap sentence is the transition matrix becomes very large. So the computational cost is very high for cluster computation. For example, if n equals 10, 2 to 10 times 2 to 10 equals around 1 million. So the number of nodes is 10 is not so large, but the component is very, very large. So it's a big problem. And their motivation is to efficiently simulate the Markov dynamics, so the infection spreading process. The authors developed a quantum computational framework. It's motivated. And then, what is quantum computer? In classical system, if a person in the box, and we don't observe in the box, this person is susceptible or infected. His or her state is determined even if we don't observe the box. And the susceptible is labeled +1 and infected state is labeled -1. It's like a bit binary. And this state can also be described as vectors. So the left panel, the vector state that is labeled 1, 0. It means only this direction. And infected state is labeled 0, 1. It's vertical direction. In classical system, the state can be only two states. So, but in the quantum system, if we don't observe the box, his or her state is not determined. It's probability. And the probability of susceptible is alpha squared, and probability of infected is beta squared. The state can be described as this, and it's called qubit, not bit, qubit. And geometrically, it means circle. So, in the classical system, this his or her state can be on circle on the edge of unit circle. It's a quantum system. But this qubit represents a probability, and probability cannot be observed directly. So how can we observe the quantum state? We can use observable operator Z. The definition is here. And the expectation value of infectious states can be described here. For example, sorry, I didn't write definition of the this row vector, and this vector is column vector, and conjugate, And for example, if the his state is 100% susceptible, this sigma is +1. It means 100% susceptible. And if 100% infected, the sigma is -1. And if his state is quantum system, the sigma is alpha squared minus beta squared. It is the expectation value. So if the 50% susceptible and 50% infected, sigma is 0. And more likely susceptible, sigma is positive. And if the probability of infected is higher than susceptible, expectation value is low, is negative. So when open the box, when the box is opened and we observed states, his or her states is determined randomly, stochastic. But expectation value is already determined before opening the box. And then another key concept is density parameters, a density operator. Density operator defined here. Using a density operator, we can calculate expectation value of infectious states as follows. So it means if we know density operator, we can calculate the expectation value of infectious states. So the state vector is not required. Only density operator is required. Okay. So we can understand how to represent a quantum state of infection. And then next question is, how do we model the spread of infection, interaction between people?
So does the red sentence means that although we don't know the exact value of alpha and beta, that by using the density operator we can get the expected value?
It means and if we know density operator, we know alpha and beta. So we don't need to use state vectors. We don't need to use this vector directly, but instead we analyze density operator. Any other question? Okay. So next question is the interaction between each other. So they use the analogy between the Ising model of spin lattice systems and infection spreading process. The using model is very well studied system. It represents magnetic field. So then I will provide intuitive image of spin system, but it's not exact. So be careful. This is the electron, and electron rotates, and then current rotates opposite direction, and then magnetic field is generated up and up direction. And then if the rotation of electron is opposite, magnetic field is down. So it's called spin. And we assume the spin state is binary, up or down. And it's labeled +1 or -1. And first, I will explain classical Ising model. Ising model it represents interaction between two components. These components, the spin of these components can be +1 or -1, up or down. And the Hamiltonian of the model can be written here. Hamiltonian, roughly speaking, Hamiltonian is energy. So this means if the system is up and up, Hamiltonian is minus gamma. If opposite direction, up and down, Hamiltonian is plus gamma. And if down and up, Hamiltonian is plus gamma. And if the Hamiltonian is same spin direction is same direction, down and down, Hamiltonian becomes minus gamma. And Hamiltonian is energy, so minus gamma is lower than plus gamma. And the same direction is stable. So in this, for this is classical Ising model, steady states are up and up or down and down. They want to be same states. Then I will explain classical Ising model. The states of spin is described using vector. It's like the infectious system. In this case, 2 qubits represents here. It's defined tensor product, but it's not so difficult. And the definition of tensor product is these components times this component times this vector is here, and beta 1 is component times this vector is local. And then 2-qubit states is represented by here. It's not so difficult. So, if we consider classical states, up and up is 1, 0, 0, 0, and up and down is 0, 1, 0, 0, and down and up is 0, 1, 0, 0, 1, 0. Down and down is 0, 0, 0, 1. It's not so difficult. In this case, Hamiltonian can be written as here. Z is Pauli Z matrix. It's a special matrix in quantum physics. I don't explain the detail, but Pauli matrix have a unique characteristics. And Hamiltonian is also defined by tensor product. So in this case, Hamiltonian can be written as this diagonal matrix. Again, why does this Hamiltonian represent the interaction between two qubits? To explain the interaction, we will consider if this Hamiltonian apply up vector. In this case, if this Hamiltonian apply up vector, it becomes minus gamma as the up vector. And if it's applied to up and down, the coefficient becomes plus gamma. And then down and up vector, coefficient is plus gamma. And if down vector, coefficient is minus gamma. So in this case, plus or minus gamma is eigenvalue. And this 2-qubit state is eigenvector. Eigenvalue is corresponds to energy of the eigenvector states. So in this case, 0, 0 vector or 1, 1 vector are stable. So using this Hamiltonian, we found up and down are stable in the 2-qubit contact spin system. So they want to be the same direction. Using the analogy between the spin direction and infection spreading, we will model the infection spreading phenomenon. We consider one susceptible person and one infected person. In this case, we use the same Hamiltonian. Using this Hamiltonian, we can calculate density operator. The time evolution of density operator is described by von Neumann equation. And this solution is here. So it's very easy. But there is problem. As I said, the eigenvalue of Hamiltonian is plus minus gamma. So this exponential function becomes exponential minus I gamma t or exponential I gamma t. So the density operator oscillates. It's unlike the infection spread and infection process. It's because this system is energy conservative and reversible. Means this is energy landscape, and this is here is up or down line. So it's energy dissipative system, and the time evolution goes to steady states. But in this case, the Hamiltonian is energy conservative. So the dynamics rotates same energy. It's a big problem. To address this issue, they introduced heat bath system. Here is the same system in previous slides, and they introduce here it's heat bath state. And this Hamiltonian is described as follows. And this term is system Hamiltonian. It represents interaction within the system. And this term represents heat bath Hamiltonian. The coefficient is different, but the structure is same. So heat bath Hamiltonian also represents the interaction between living heat bath. And third term is interaction between system and heat bath. It's a little bit difficult. X is a power X matrix. So what is the heat bath? To explain heat bath system, we consider we neglect the right network, and we consider only system and heat bath, two components. And this slide is not exact, it's intuitive, so be careful. And in this case, 2 qubits is the state of system and state of heat bath. And Hamiltonian is here, it's from this. Hamiltonian can be written Pauli X matrix. It's defined by tensor product. So x times x is this type of matrix. What does it mean? Intuitive interpretation is here. If this matrix applied to 0, 0 vector, it can be 1, 1 opposite. And if it applied to 0, 1 vector, it can be, the vector can be 1, 0 opposite direction. And if it applied 1, 0 vector opposite, and it applies to 1, 1 vector opposite 0, 0 vector. In general, if we apply XX operator, the probability becomes opposite. It means x times x exchange the infectious states between the system and heat. Exchange. And then time becomes infinity. This system converges thermal equilibrium, which means the state of system equals state of heat bath. Intuitive explanation is the square is this room, and we a cup of coffee. The room temperature is 20 degrees, and the temperature of coffee is 60 degrees, and energy is exchanged between coffee and room. So after 1 or 2 hours, the temperature of coffee is 20.1 degree, and room temperature becomes 20.1 degrees. So temperature becomes same. In this case, energy of whole system, energy of coffee and room is conservative. But the energy of coffee is dissipative. So that's why heat bath system represents energy dissipative and irreversible state.
So what is the reading of temperature in this system?
Temperature, it's very intuitive, but in this case, the temperature means probability. Probability.
So system will be moved to the specific height. In this example, the room temperature is high.
Yeah.
So what is the direction of this system?
Each other. The direction is direction is each other. This direction and this direction. And the probability of the states is exchanged. If the system is
System heat bath has a room temperature, right?
Yeah.
Then the local system will be moved to the change to the total heat bath temperature, right? So what is the room temperature in this system?
and in this system it's probability. Probability is exchanged. If 100%, and if the system is 100% susceptible, next time heat bath is 100% susceptible. Heat bath is sorry. Yeah, it's okay. If the system is susceptible, heat bath becomes infected. But in this case, so it's not exact, but intuitively, the probability of infectious disease is exchanged. For exact understanding, we have to understand entanglement. It's difficult, but intuitively, the probability is exchanged. It corresponds temperature. Any other questions? And then using heat bath system, Hamiltonian is formulated as follows. And then in this case, total density operator is written as here. It's energy conservative and reversible. But system density operator is energy dissipative and reversible. And TRB means choose the TRB means choose the trace of system state and remove heat bath state. It's partial trace. So using Hamiltonian, we can calculate system density operator. In this case, we assume one susceptible person and one infected person. And then next, we consider network. it's S susceptible people and I infected people. But in this case, Hamiltonian, the structure of Hamiltonian is same. But it's at sigma, but its structure is same. In comparison with SI model, there's the classical deterministic SI model. Gamma ij in the Hamiltonian corresponds to contact patterns. So gamma ij represents heterogeneity. And lambda corresponds to virus transmissibility. It's represents nature of virus. And then using this Hamiltonian system density operator can be written here. This matrix is 2 to n by 2 to n matrix. It's still large matrix. So quantum computer cannot compute. It's difficult to compute this matrix using quantum computer, but classical computers. But quantum computers can compute this density matrix easily. So this is the advantage of quantum computer and this formulation. And then, but the next question is, how can quantum Ising model simulate classical Markov chain model? In the first part, I explained quantum system is in quantum system the infectious state is stochastic, but in our real world we are 100% susceptible or 100% infected. It's different between classical system and quantum system. So it can be explained using density operator. In quantum system, diagonal component is classical component. The non-diagonal component is quantum part. So in classical system, only diagonal component is non-zero, and the non-diagonal components are zero. So if we choose the initial state is classical, non-diagonal part is zero, time evolution of density operator is classical. This non-diagonal part is always zero. That's why we can compute classical system using quantum system. This is the methodology. From this slide, we will show the simulation results. In this figure, we consider one susceptible and one infected, the simplest case. And the parameters are alpha equal pi and gamma equal pi. The author theoretically derived this parameter is optimal using perturbation theory. Alpha equal pi is optimal, but I don't understand. It's very difficult, but they choose optimal parameter, and then they change parameter lambda. If the lambda is small, the slope is not steep, it's flat. But if the parameter lambda is large, the dynamics is exponential decay. It's quantitatively similar to SI model. And in Omicron strain of COVID-19, P1, the vertical axis is the survival rate. Sorry, I didn't write the image. The vertical axis means the fraction of the susceptible people. So in the Omicron strain, after 1 week, 25% of susceptible people is infected. So P1 of 7 is 0.749. In this case, lambda is 0.201. So they can estimate the parameter value. Finally, I will show you more complex network, small network. And they consider this point is one patient, and orange field is 4 susceptible people. I think it's family, and the node 2 is population 95 susceptible people. It's company, and 100 susceptible people is other community, and node 4 is 200 susceptible people. It's like city. The Hamiltonian is defined as here. And they assume contact pattern, the interaction with each other follows Gaussian distribution, like here. And then parameter setting is alpha is optimum value, and lambda is Omicron states. And gamma is depend on distance. Gamma is determined to satisfy this equation. It is from perturbation theory. They analytically, theoretically derive this relation, but I don't understand. So anyway, they can estimate the parameter value of gamma using this equation. This is the settings of the simulation. Here is the results. The color is infection probability. In this case, the the infected people is confined this area. And they thought other situation. One infected patient and one infected patient. In this case, the infection spread more rapidly. Here is the real date of infection spread in the US. I don't know how to compare the they states qualitatively similar. I don't know, but it's qualitatively similar. In summary, in this paper, to efficiently compute the Markov process of infection spread, the quantum Ising type infection Hamiltonian was constructed, and to reproduce energy dissipative and irreversible dynamics, interaction between a heat bath was introduced, and the quantum Ising type infection models simulated qualitatively similar pattern to the infection spread in the US. In this paper, they consider only SI model, but they said this approach can be extended to SIR and SEIR model using more qubits. So in the future, maybe in their future work, they can analyze SIR model or SEIR model, more realistic model. That's all. Thank you.
Thank you for this. So they set some heat bath, right?
Yeah.
So heat bath should have specific room temperature. So the local system eventually move to the state of the local system should be changed to the bad state, right? State in the bad.
Yeah.
So I wonder which state is majority of the state of the heat bed. What is the majority?
I don't know.
All impacted or
I think it depends. Alpha represents heat bath. So, but I don't know the detail.
but in the last simulation results show that on the heat map. This simulation showed that the system is moved to the all impacted. So somehow they said the heat bath system is all impacted system.
Yes, heat bath system is interactive with.
Interactive, but the heat bath also have a. They assume that the heat bath is a large system, right?
No, not large.
Not right.
It's same size.
Same size.
Same size.
The system, how the system moved to the all impacted direction.
All infected. But it's not all or infected. The probability is very, sorry for it's tiny. It's 0.25. So the state, not all the state is infected.
But in previous, but yeah, yeah. The curve
Maybe
is vibrating zero.
the interaction is large. The equilibrium is zero or all infected. But I think lambda is small. Equilibrium is not zero. Maybe I don't know. They will until here. Thank you. Any other questions or comments?